All right. Hey, everybody. Today we're going to be talking about the Williamson ether formation. This, again, is an alcohol reaction. It's one of the reactions at O, also called O alkylation. And this is a second semester organic chemistry reaction. So, the history of this is that it was discovered in 1850 by Alexander William Williamson. What a crazy name. He is an English chemist who helped establish modern ideas about ether structure. And that is him right there on the right. So he studied under another chemist, Justus von Liebig, and he later became a professor at University College London. So essentially, this reaction was going to use an alkoxide ion as the key reagent and a primary alkyl halide as the electrophile. The reaction is going to happen via an SN2 process, displacing the halide leaving group. And I kind of have a song about it. It's like SN2 backside attack is true, SN1 carbocation. So we know this is going to have a backside attack. So, overall transformation, the formation of an ether is going to be created by a new carbon oxygen bond between the two organic groups. So, now let's get a little bit into the mechanism of this presentation. And I'll start by loading up something to draw with. All right. So, let's say we have a cyclohexanol thing going on here. Okay. So, we have this, and we're going to have our reagents. Let's say we have this. We have NaH as our first. And then as our second reagent, we're going to have, let's say, this. And we're going to have a little bit of stereochemistry going on here. Just to make it interesting. Okay, let's say we have this. So first, I want to make this really clear that it's going to be Na plus H minus. Everybody knows, hopefully, that we have a bit of a charge there. So our first step is that we're going to take this charge, and the charge is going to attack the hydrogen here, causing these electrons to carry over to the oxygen. So that means we are going to get this, our alkoxide. So now we know that floating around in there, we have this bromine group here. So I made the wedge really big, but we get the gist that this is a wedge. So what's going to happen is, like a typical SN2 fashion, we're going to take this. It's going to do a backside attack and attack there, causing this to move up. So we know that when an SN2 reaction happens, we get inverted stereochemistry. So that's why that whenever we draw our final product, is going to look like this. See? Oops, I'm sorry. I actually made the wrong thing. So think about it. Because we have inverted stereochemistry, we have to be very clear about the fact that we are going to have our inverted structure. So the way I drew it was not correct. We want it to look like this, because the structure is inverted. If I drew it the way I wanted to draw it in the first place, it would look more like this. These are the same. I'll kind of write that out to you. Equal. You have this. You could have this. Oops. I meant to draw a wedge. I'm sorry. So you have the wedge here. The wedge, like this. And then we would just have the one here. And then these would be our two options. You see how they're different? But this is the one with the inverted stereochemistry. Okay. So now let's go ahead and do some predictive product questions. Okay, so we know that what's going to happen is that it's going to do that backside attack like we just showed before. So we're going to have the alcohol here. We're going to make an ether. So essentially we have the R group that's going to join. So we know that the answer is going to be OR. So part of it is just identifying what is the halide and what is the R. So this I is the X part, and then this here is the R. So we have I attached to the R. So we can think, what does that mean? So that means that what's going to be attached to the alcohol, or the oxygen, I'm sorry, is just going to be a methyl group. So that's our first answer here. And we could do the same thing here as well. So we see this is the X, and then here we have our R group. So again, we know that what's going to be attached is going to be the R group. So we have this, the and then here we have 1, 2, 3. So we're going to do 1, 2, 3, 1, 2, 3. This is what we're going to have joining. This is our final answer. Okay, and we can do that again here. So let's say we have our ring, our aromatic ring here. We're going to have our oxygen. And again, we have our X group here. And the rest of this is the R group. So we're going to have to join this with the R. So those are our answers to 3 predicted products. And then let's do these two. Okay, they're a little blurry, but again, we have a bromine, and the bromine is the X. Then we have this methyl group is the R. So what are we going to do? We're going to go like this. The O, and we have the methyl group. And then here, let's think about the same thing. This is a little bit more of a hassle to draw, but I'll draw. So we have the NH here. And then we're going to have our aromatic ring. And forgive me how bad it's drawn. Okay. So we have to think, what is the X and what is the R? This is the X, and then this is the R, this ethyl group. So that's essentially all we have to add on to it. We have the O, and then let's draw an ethyl. There we go. And that is the answer to those. I hope you understood the Williamson ether formation. It's all about just identifying what's the X and what's the R and putting it together as an ether. Thank you.